The AI chip industry. It's the engine that powers our entire technological future. But what if I told you that its very foundation is starting to show deep fractures? We're going to deconstruct the technology, the commercial dynamics, and the geopolitical forces that are fundamentally reshaping this critical global arena.
So let's start with the conclusion right up front. The single most important takeaway is this. The era of a unified global supply chain for AI chips, well, it's over. We are witnessing a structural split into two distinct competing ecosystems. And that shift changes the calculus for everything, for technology, for trade, and for global power.
To really understand how we've arrived at this pivotal moment, our analysis is going to cover 5 key areas. We'll start with the core technology itself, then deconstruct the global supply chain, look at the major corporate players, analyze the divergent market logics, and finally, lay out the framework for this new world of two systems.
Okay, first up, what exactly is an AI chip, and what makes it so different from the traditional processors we've used for decades?
Unlike the general-purpose CPUs in your computer, which are designed to handle tasks sequentially, one after another, AI chips are specialists. Their entire architecture is purpose-built to run a massive number of calculations all at the same time. And that is exactly the kind of parallel processing that modern artificial intelligence algorithms demand.
So the market really breaks down into 3 primary designs. You've got GPUs, which are the flexible workhorses, ideal for that complex, messy process of developing and training new AI models. Then you have ASICs, which are custom-built for one single function, giving you maximum efficiency when a model is deployed at a massive scale. And somewhere in the middle are FPGAs, which offer a reprogrammable balance between the two. Each one represents a critical trade-off between power, flexibility, and, of course, cost.
You know, a really effective way to think about this is the university versus the factory. Training an AI model is like sending it to university. It's experimental, it's incredibly resource-intensive, and it needs the versatile power of GPUs. But inference? That's the factory floor. That's where a fully trained model performs its specific job millions and millions of times. And on the factory floor, the specialized efficiency of an ASIC or the speed of an FPGA is what truly matters.
Now, this industry didn't just pop up overnight. For decades, the theory of AI and the invention of the microchip were evolving on these separate parallel tracks. The really critical moment, the inflection point, came in 2012. That's when researchers used a simple gaming GPU to train an AI and achieved a jaw-dropping breakthrough in performance. That was the big bang for the modern AI era. And then, of course, in 2022, ChatGPT created a demand shock for computing power that the industry is frankly still scrambling to meet.
So, how are these unbelievably complex chips actually made? This brings us to the global supply chain, and more importantly, to its critical choke points. This entire value chain is defined by one thing: hyper-specialization. Upstream, you have the intellectual property and the complex design software. The midstream is the incredibly capital-intensive world of physical manufacturing. And then downstream is where these chips are actually integrated into servers and applications. Getting into any one of these stages requires decades of expertise and just an immense amount of capital investment. And right here, this is where we find the first critical choke point: design. It is functionally impossible to design a modern complex chip without using software from one of 3 Western companies: Synopsys, Cadence, or Siemens EDA. That's it. Together, they form a powerful and incredibly defensible oligopoly.
The second choke point is in manufacturing. When you're talking about the most advanced chips, those with nodes under 7 nanometers, one company has a commanding, almost unbelievable lead: Taiwan's TSMC. It controls over 60% of the market, with its closest competitor, Samsung, way back in a distant second place.
But even within manufacturing, there's a monopoly that's even more absolute. The Dutch firm ASML has 100% market share in the extreme ultraviolet, or EUV, lithography machines. These are the machines required to produce those leading-edge chips. Control of this single piece of equipment is a strategic lever on the entire global semiconductor industry. It's that simple.
So it's no surprise that this highly concentrated supply chain has, in turn, created a very clear hierarchy of corporate players on the world stage.
Now, NVIDIA's dominance isn't just built on superior hardware. That's only part of the story. Its real moat is its proprietary software platform, CUDA.
For over a decade, AI developers have been building their tools on top of this ecosystem, which creates powerful network effects and really significant lock-in. Challengers like AMD are trying to counter this with open-source alternatives, but convincing an entire industry of developers to retool, well, that is a monumental hurdle.
At the same time, U.S. export controls are actually accelerating the rise of domestic champions in China, like Huawei and Cambricon. Now, their primary value proposition isn't necessarily about beating global competitors on raw performance. It's about providing a secure, resilient supply chain that cannot be disrupted by geopolitical factors.
And you know, the clearest evidence of this fracturing, of this split, can be seen when you look at the divergent logic of the world's major financial markets.
In the U.S. market, performance is really measured by one simple metric: global technological dominance. NVIDIA's 56% revenue growth? That's a direct function of its command over the global data center market. The performance of its competitors is judged by that exact same ruthless global standard.
Now, in stark contrast, China's A-share market operates on a completely different logic. The key driver here is a term you hear over and over: domestic substitution. Cambricon's extraordinary revenue growth, over 4,000%, is not a function of global expansion. It's about capturing the vast domestic market that is now insulated from foreign competition. This is, through and through, a policy-driven market.
Okay, so let's pull all of these threads together. Let's synthesize these findings into a coherent framework for understanding this new bifurcated industry.
So here's the crucial takeaway. A single analytical model is no longer sufficient to evaluate these companies. It just won't work. In the US, the logic is based on global tech leadership. In Hong Kong, a company like SMIC is assessed on its strategic necessity to national objectives. And on the mainland A-share market, the core driver is policy-driven growth inside a protected domestic ecosystem. 3 different markets, 3 different sets of rules.
And looking ahead, the competitive landscape is going to be defined by 3 emerging battlefronts. First, we'll see a shift in the economic gravity away from training models to deploying them efficiently at scale. That's inference. Second, a huge push for AI on the edge, putting it directly into our consumer and industrial devices. And finally, as we reach the physical limits of transistor scaling, advanced packaging techniques like chiplets will become the new frontier for performance gains.
And all of this brings us to the fundamental strategic question. With 2 separate ecosystems for research, development, and deployment, what happens next? Will innovation actually accelerate because of heightened competition, or will it be constrained by fractured standards and duplicated effort? Where the next great breakthrough comes from, that is now the defining uncertainty in the world of technology.